This is the Unit 1 practice exam for Math 1050. So question number 1 is from section 2.1, the difference quotient. What I suggested doing first is evaluating f of x plus h for the function. Now, this function has two places with variables, x squared and 2x. Remember what I suggested is anytime there's a variable, make an empty set of parentheses. And then the x plus h fills in the parenthesis. And we got to simplify this. So that's f of x plus h. This expression here is what's going to replace f of x plus h here on the top left part of this fraction. So the difference quotient is just big fraction with h on the bottom. This expression here is what's going to be written in the top left. And then we need to subtract an entire function. And like I said in class, when you're subtracting a function, the safest way to do that is to subtract the function in a parenthesis. And then you combine like terms. So this negative x squared, and I say negative because remember this minus sign is going to distribute. X squared is going to cancel here. Negative 2x is going to cancel with that 2x. And then negative 4 is going to cancel with that 4. So then what's left over in the numerator are only terms that have h as a factor. And then if we factor out an h in the numerator, then the h's cancel. You have 2x plus h plus 2 as the difference quotient. Question 2 is also from section 2.1, finding the domain of a few different types of functions here. What we talked about for these functions, rational functions, is we need to first focus on the denominator because that's where we're going to have exclusions from the domain, and it needs to be in factored form. So first step would be to factor the denominator. And that's going to factor into x minus 2, x minus 3. So from that, we can conclude that x cannot equal 2 and x cannot equal 3. And I always like to write it down so I don't forget. You don't necessarily need to write it, but x cannot equal 2, x cannot equal 3. And now from that, we can build the domain. Domain is every other value except x equals 2 and x equals 3. So that's from negative infinity to 2, and then from 2 to 3, and then from 3 to infinity. Now this second function here on part B, it's still rational, and so we want to focus on the denominator, x cannot equal 2, but the numerator is a radical expression. And what we talked about with radical expressions, square roots and fourth roots, anything with an even root, the expression underneath needs to be greater than or equal to 0. So there's two pieces we need to consider. From the denominator, we can conclude that x cannot equal 2, but in the numerator, any expression underneath the square root needs to be greater than or equal to 0. So 2x minus 1 needs to be greater than or equal to 0. And if we add 1 and divide by 2, we get x is greater than or equal to 1/2. So there's two statements here that we need to reconcile into one domain statement. Here this says x can only be greater than or equal to 1/2, but also cannot equal 2. And again, this wouldn't be part of what you would need to do, but sometimes it's helpful to visualize what the domain is on a real number line. So if the domain starts at 1/2 with a filled in circle, and greater than that means to the right, but once we get to +2, we have to exclude it with an open circle and then keep going. So what we see here are two intervals. There's an interval from 1/2 to 2, and then from 2 to infinity. So the domain, including 1/2, so there's a bracket, to 2, and then from 2 to infinity. Question 3 here is from section 2.2. In this one, we're graphing a piecewise function. The way I suggested that this be done in class was to look at each piece individually and make a table of values for just that piece. So if we're going to make an XY table of values for that top piece, then we have to choose our domain based on this domain description here. It says x has to be strictly less than -2. Now, if you remember our discussion in class, it's always a good idea to include these boundary numbers here, like -2 or -2 and 1 and 1 here. You want to include these boundary numbers in your table of values. Even though here it says x is strictly less than -2, I still want to graph a point at -2, and just remember that it needs to be an open circle. So I am going to include -2 as an x value, and then any other x value that's less than -2, so -3, -4, and so on. So this table of values is only relating to this top piece. So if I plug in -2 then into the function for x, -2 plus 2 is 0. If I plug in a -3 for x right here, -3 plus 2 is -1. And if I plug in a -4 for x, -4 plus 2 is -2. So now I've got 3 points I can graph, -2, 0. And remember, that's where I'm going to place an open circle, because x cannot equal -2 here. It has to be just less than it. The -3, -1, and -4, -2. And it has to be pointing in the left, because x is less than -2 in this direction. Now the middle piece, here, I'm going to make a table of values. And the domain descriptor here says x is between -2 and +1. So I want to start with -2 and end with +1, and you can do a few values in between, like 0. Those are your x values. And then you are going to plug these x values into this piece of the function, but there isn't a variable to plug anything into. There is only one possible output value, -3. So -3 is going to be your output for every input in that piece of the function. And then at -2 and at +1, since it equals or includes both of those, then these can be closed circles at these two endpoints. So -2, -3 is a closed circle. 0, -3, 1, -3. So it's just a horizontal line between -2 and +1. Now this piece here, this bottom piece, if we did a table of values for that, it says we need to choose x values that are greater than 1. Not greater than or equal to 1, but greater than 1. But again, we always want to include that boundary number in the table of values, and that's just going to be an open circle there. And then anything greater than that, so 2, 3, and so on. Plug in those values here. 1 squared is 1. 2 squared is 4. And 3 squared is 9. And just remember, that's an open circle on 1, 1. And then 2, 4, 3, 9. So this is just the right side of a parabola. Question 4 is from 2.4. Well, except for part D, a one-to-one function, that was from 2.8, but most of this is from 2.4. So first we need to evaluate the function f of 1, find f of 1. Now, if we had the equation for the function f, we would just plug 1 in for all the variables. We don't have the equation, we have the graph, obviously. So what we talked about in class was this is the input, or x value. So to find f of 1 just means find the y value that has this number as its x value. So when x equals 1, which is right here, the y value is 3. So f of 1 is equal to 3. Okay, for part B, domain and range, the domain is the set of all possible x values or input. So we're looking on the x-axis. So anything that's less than -4 is not going to be in the domain because there aren't any function values or there's no pieces of the graph to the left of -4. So -4 is the first input or the lowest value input that produces an output. So -4 is in the domain. All of these values from -4 to -3 to -2, all of these values are in the domain all the way up to +4, but since there's an open circle on +4, we're not going to include that. We are going to include -4 because it's a filled-in circle. So the domain would be -4 to +4 with a parenthesis around +4. Now the range, we're going to look on the y-axis because the range is the set of all possible outputs, or y values. So y values, there aren't any y values on the graph that are higher than +3, nor are there any y values on the graph that are lower than -3. So -3 is the lowest bound all the way up to +3, which is the upper bound. And we need to consider now, do we use parentheses or brackets? Well, is 3 in the range? Is there a point on the graph where 3 is the y value? And the answer is yes, 1, 3 or -3, 3. So 3 is in the range, so we're going to include 3, as well as -3. So we go to this point, 3, -3. -3 is a point, a y value on the graph. So -3 is also included. And remember, you always do the lowest value first. So -3 comes first, +3 comes last, both included in the range. Now, intervals of increase and decrease. Remember, we only use x values. So this piece of the graph, we always read a graph going from left to right, and we consider what the y values are doing. So this piece that I'm highlighting in red, the y values are increasing as we move from left to right. So that's increasing. Starting from here up to here, it's increasing, and from here to here. So all of these values that I've highlighted in red, those are increasing parts of the graph. So what we need to figure out are what are the x values on which that's occurring. So between -4 and -3, we're increasing. Between -1 and +1, we're increasing. And between 3 and 4 on the x-axis, we're increasing. And I am going to use parentheses here to describe all of these intervals where the graph's increasing or decreasing. So from -4 to -3, and again, these are only x values from -4 to -3. Also from -1 to +1, and from +3 to +4. Now, portions of the graph where it's decreasing, I'm going to highlight those in blue. There's a decreasing portion of the graph and a decreasing portion of the graph. So remember, we don't describe that from a point to a point. It's only values on the x-axis. So from -3 to -1, and from +1 to +3. So the intervals of decrease would be from -3 to -1, and from 1 to 3. Now part D is the function 1 to 1. It is a function because it passes the vertical line test, but what we talked about in section 2.8 is for it to be 1 to 1, it needs to pass the horizontal line test, and this does not. It fails the horizontal line test. So it is not 1 to 1. And if you needed to explain that, which it would be a good idea to be prepared to explain that, it fails the horizontal line test. So for question 5, we need to determine if this function is even, odd, or neither. The way we do that is by evaluating the function at negative x. So in the original function, anytime there's an input, I'm going to turn that input into negative x. And here with negative x raised to the third power, multiplied by 4 is negative 4x cubed. And then negative 2 times negative x is positive 2x. Now, what I'm noticing here is every term is the exact opposite of the terms from the original function. So I'm actually going to factor out a negative sign. What I have written in parentheses here, 4x cubed minus 2x, is the original function, and we have the opposite of that. So what happened is at f of negative x, it ended up being the opposite of f of x, meaning when I plugged in negative x into the function, that ended up giving me the exact opposite of the original function. This is an indication of an odd function. Okay, for question 6, we need to write the equation of a function that has these transformations. The parent function is cube root of x. I'm just going to use a new name here, g of x. So this one's going to have reflected across the x-axis, meaning it's flipping up or down. That's a vertical reflection, so that needs to occur outside of the function. Now it's going to be shifted to the left. That's a horizontal shift, so that needs to occur inside the function. So x plus 3, and then it needs to move up 2 units, so that's going to be a vertical shift up 2 units outside of the function. Okay, question 7. This is an absolute value function. Typically, for absolute value of x, the vertex is here at 0, 0, and it's pointing up like this. This one has transformations 2 units to the left, 1 unit down. We also have a vertical reflection here, so the graph is going to flip upside down, and then this is a vertical compression by a factor of 3. So let's start with where the vertex is. It's 2 units to the left and 1 unit down. Okay. What I'd recommend from here, we know it's going to be pointing down kind of like that, but we need to have the exact width. So what I'd recommend is just make a table of values. We already know 1 point, it's the vertex, negative 2, negative 1. So I'm just going to plot a few additional points. Now, whatever comes out of the absolute value is going to be multiplied by 1/3. So I want to be careful with what I choose for x so that this turns out to be a multiple of 3. So then you can divide it by 3. So I'm going to let x equal 1. If x equals 1, 1 plus 2 is 3. Absolute value of 3 is 3. 3 times 1/3 is 1. 1 times negative 1 is negative 1. And then negative 1 minus 1 is negative 2. So 1 comma negative 2 is on the graph. Now, absolute value graphs are symmetric, so we can reflect this point over the line of symmetry to right here. So we have a third point on the graph, negative 5 comma negative 2.
Question 8. This is from section 2.7, combining functions. For part A, we're going to add the two functions together. In order to do so, we need to have a common denominator. So for the one on the right, I'm going to multiply by x minus 2 over x minus 2. The one on the left is going to be multiplied by x plus 1. So then this numerator becomes 4x plus 4. This numerator becomes 2x minus 4. So now that we have a common denominator, that common denominator is x plus 1 over x minus 2. And then we combine like terms in the numerator, so that's going to be 6x. And we have a 4 plus negative 4, which is 0. Part B, f minus g of 2. This can be thought of as f of 2 minus g of 2. The problem here is f of 2, 2 subtract 2, f of 2 is undefined. So we can't subtract g of 2 from something that's undefined, so the whole problem is undefined. For part C, f multiplied by g is just f of x multiplied by g of x. So we're going to have 4 over x minus 2 multiplied by 2 over x plus 1. Nice thing about multiplying fractions is you just multiply straight across. Okay, part D. F divided by g of x is f of x divided by g of x. So f of x divided by g of x is the same thing as a multiplication problem. Multiply it by the reciprocal of the denominator, and then multiply straight across. Now part E is g composed with f of 4. We can think about that as g of f of 4. So the first thing we need to find is f of 4. So f of 4, this is the f function here. If we plug in a 4 for x, 4 subtract 2 is 2, 4 divided by 2 is 2. So 2 is going to replace f of 4. So this becomes g of 2. Now, this is the g function here. 2 over x plus 1. So if x is 2, 2 plus 1 is 3. 2 divided by 3 is 2/3. Okay, part F. What's the domain of the result of part A? So we're going to exclude -1 and +2. -1, +2. So if we're taking that out of the domain is everything else, which means it's from -infinity to -1, and then -1 to 2, and 2 to infinity. Now part D, if we just look at the result, it would appear that the only exclusion is x equals 2, but we have to look at also the exclusion right here. We can't have a -1 in this denominator, otherwise the function would be undefined. So we also have to exclude -1. So we're excluding -1 and +2. So it's actually the same answer as for part F. Okay, question 9. We are finding the inverse of the function, so we're finding the inverse, and then state the domain and range of both. That means we have to have the domain of f of x and the domain and range of the inverse. So if we have the original function, and we switch the place of x and y, that's the first step. Remember, you can think about that as y. So the first step is to switch their places. And if we're solving for y that's in the denominator of a fraction, we cannot solve for a variable that's in the denominator. And typically we really don't want to solve equations that have fractions in them anyway. So one thing we can do is to get rid of the fractions by multiplying both sides by the denominator. That's going to clear the fraction. So the left side, we're just going to have y minus 2 multiplied by x is equal to 3. Now we can divide by x. So what that's going to give us is y minus 2 is equal to 3 over x. And now we can add 2. And that's going to give us y equals 3 divided by x plus 2. And this is equal to the inverse. Now going back up here for the original function, the domain is everything except for positive 2. Range is more difficult to find if all you have is the equation. So we're going to go down here actually to the inverse and find the domain of the inverse, because if you remember in class we talked about the domain is the range of the original function, because we find the inverse by switching the place of x and y, and domain and range are just x and y values. So the set of x values for the inverse is the set of y values for the original function. So the domain here is all values except for 0. We can't divide by 0 from right there. So that domain is negative infinity to 0 and 0 to infinity, which means that's the range here. And then if this is the set of x values for the original function, that becomes the set of y values for the inverse function. And that's from section 2.8, by the way. Number 10 rather, also from section 2.8. The suggestion was to, well, make a table of values, because when you graph an inverse, all you're doing is switching x and y values. So if we have a table of values for the original function f, I'm just going to locate these points there. So we have negative 5, 0, 0, 5, 2, 1, and 5, 2. So the inverse then, we're just going to switch the place of the x and y values. So I have 0, negative 5, 5, 0, 1, 2, and 2, 5. And if you remember in class, we talked about the original function and an inverse being a reflection across that line there, y equals x.